Hi everyone, thanks for coming to this talk. My name is Paige Randall North, and today I'm going to be talking about joint work with Benedikt Ahrens, Michael Shulman, and Dimitris Tsementzis on a higher structure identity principle. And before I begin, just want to point out that the slides are available at this address in case you want to jump around in them while you're listening to this talk. Okay, so first I'm going to begin with some philosophical motivation. So I'm going to talk about synthetic versus analytic equalities. In Martin-Liff type theory, which is what we're interested in, we always have a notion of synthetic equality, which is just given by the usual notion of equality in Martin-Liff type theory. And I call it synthetic because we can't decompose it at all, just is stipulated. But depending on the type T, say we're interested in groups, we might also have a notion of analytic equalities, which I call analytic because they can be usually decomposed or built up from pieces. So in particular, in the case of groups, we might be interested in group isomorphism, which consists of two functions or two homomorphisms back and forth that compose to the identities. And both of these notions of equalities have their pros and cons. So the one given by Martin-Liff behaves very nicely, very easy to use. This one is generally harder to use, but maybe easier to get. It's usually the one that we get from usual mathematical practice. So we are interested often in tying these two together so that we get the best of both worlds. And we would call this, I would call this a univalence principle. So for a particular type T and a particular notion of analytic equality, we might say that the univalence principle would say that this map, which always exists between the equality type and a given other notion of sameness, is an equivalence. Okay, and so the word univalence might sound familiar to you, and if you're not exactly sure why, I just want to point out that the univalence axiom proposed by Vladimir Blavatsky states that the type of equalities between two actual types and the type of equivalences between them are the same. So we're supposing that this principle, this axiom, holds in our work, and we want to extend this to not only types, but other things, in particular, other kind of algebraic structures like groups and categories and higher categories. Okay, so why in particular do we want to do this? So I want to invoke some philosophers. So first of all, Leibniz said when he was wondering when we might be able to say that two things are equal, he said that two things are equal when they are indiscernible, meaning they have the same properties. So if we have a property P and P of A holds whenever P of B holds, then we want to say that A is the same as B. But of course, this seems to presuppose the rather obvious remark that if two things are equal, they should also have the same properties. So this should actually be part of a by implication. And as type theorists, we can beef this up a little bit, change the for all to a pi type and the by implication to an equivalence. And this statement does hold in MLTT. So whenever we have, in particular, whenever we have an equality between A and B, we know that they have the same properties. And so if we have an equivalence principle, like I talked about in the previous slide, then we could compose these two things and find what Axel called a structure identity principle, which is to say that if A and B are analytically equal, so in the case of groups, if there's a group isomorphism between A and B, then they should have all of the same properties. And this is something that is not provable in ZF. Of course, you can find weird kind of non-group theoretic properties of two groups that differ between isomorphic groups, but it should hold, and in practice, group theorists, of course, assume that it holds for all group theoretic properties of two groups. So we want to see this, this kind of guiding principle in mathematics that isn't provable in normal foundations like ZF as being provable in univalent foundations. Okay, so the univalence principle for groups is provable, as I suggested, and it was proven in a more general framework by Gokhan and Danielson. So for two groups, G and H, their equality type is the same as the type of group isomorphisms between them. And this, as I I remarked before, immediately gives us a structure identity principle for groups, which is to say, if we have two isomorphic groups, then they must have all of the same properties. And it's interesting that in type theory, we can't find a weird set theoretic property P that would distinguish two isomorphic groups G and H. Okay, and in further work by Ahrens, Kapolkin, and Shulman, they showed a univalence principle for categories, but not for all categories. In fact, it's false in general for all categories. It's only true when we consider univalent categories. So we have this equivalence principle for univalent categories, and what are they? Those are categories in which the type of equalities is identified with the type of categorical isomorphisms between any two objects, x and y. Okay, so for univalent categories, we have the univalence principle. And so maybe I should remark that this definition of univalence category is imposing a univalence principle inside of the category. And from that, we get a univalence principle without, like, outside of the category. So there's an interesting relationship there. But from that, we automatically get a structure identity principle for categories, which says that if we have any two equivalent categories, C and D, then they must have all the same properties. Okay, so our goal and our result was to define a large class of higher structures that encompasses groups and categories, but also higher categories and other notions of structured categories. Notions of univalence that from the formulation of the different structures automatically comes out, and also an automatic notion of equivalence between them, which validates the univalence principle in the sense that if we have two univalent structures, the type of equalities between them will be the same as the type of equivalences between them. And then from this, we automatically get a structure identity principle. So in this work, we're using and building on ideas from Mackay that he wrote about in his paper, First Order Logic with Dependent Sorts. And as I already mentioned, we're also using the work that was begun in the Ahrens, Kapolkin, Shulman paper on univalent categories and the res completion. And I want to point out that there's an expanded preprint of this work on the archive here at this address. And there's also an expanded, more pedagogical talk that has recently been given at this address. Okay, and in that expanded preprint, we have many examples of structures where we work out what all of these notions distill to. So we have dagger categories and bicategories and thunk force categories and many more. So if you're interested, please look at the paper. Okay, so now I want to explore our ideas in the context of folds categories, or categories in particular. But first I need to define what a signature is. So a signature, first of all, consists of an inverse category, which is to say a category and a functor from that guy to nat op, whose fibers are discrete. And what that boils down to is saying that we have a category like this, and we have a way to stratify this category into levels that are labeled by natural numbers. And once we've stratified it in this way, all the arrows must point downwards. And saying that the fibers of that functor are discrete just means that we don't have any horizontal arrows. Okay, and then we can describe the height of any category like this. So this guy has height 1 because the highest level is at 1. And for any signature that might be much higher, we say the height is just the maximum level. And in this work, we're only considering inverse categories of finite height, so we call those signatures. And here we have two examples. So here's a signature for graph, and here's a signature for groups. Now I'm going to explain what's going on, in particular in the case of categories. So here we have a signature for categories. So what do all of these things mean? Well, if you ignore these two guys and just focus here, it might look familiar. So the signature is telling us that we need a type of objects to define a category, also a type of arrows, a source and a target of each arrow. And then we have these two things which we should think of as predicates on arrows. So I is a predicate saying that this guy is an identity arrow, and we impose some relations on these composites. So in particular, if you remember category theory, an identity arrow only goes from one object to itself. So we impose that these two composites here are equal. And we think of T as being a predicate. So T is a ternary predicate on arrows. So if we think of T of, say, FGH, we think of that as a predicate saying that H is a composite of F and G. And for that to make sense, for that to be a question that you might ask, is H the composite of F and G? You need the domains and the codomains to line up in the right way. So for example, we would require that this first domain of F is the same as the domain of H, and so on and so forth. Okay, so that's this category, and they've given you an idea of what these guys are going to pick out. And so what they're picking out is given over here. So what's happening is that we're thinking of a structure for this signature as being a functor from this category into the universe of types. But we're not going to write it down that way because we're doing dependent type theory, so we're going to write things down as dependent types instead. Okay, so what is the structure for the signature? Well, as I suggested, it's a type. So let's say the functor is C, so it's a type CO. And then instead of just saying it's a type CA, we're going to specify its fibers. So for every two objects, say X and Y of O, we have a type CAXY. So that's given here. And for every object X and every F in CAXX, we have what we should think of as a predicate I of F. So that's here. And for every three objects XYZ and arrows FG and H between them, then we can look at the predicate T FGH, saying that H is the predicate, or sorry, H is the composite of F and G. Okay, so all of that data doesn't quite make up a category because, of course, we need to impose a bunch of axioms. And in particular, you might want to add an axiom like this that's saying that this ternary relation T that's giving us a composite is actually a function. So it's saying that if we have that H is a composite of F and G and H prime is a composite of F and G, then H and H prime should be the same. But we want in these axioms to just stick to notions that are defined in our signature. So in particular, we don't want to use equality, really, because it's not defined in our signature. So to ameliorate that, we add a predicate for equality. And now to get a structure for the signature, we're going to need a family of types like this. And now we can replace this equality with an E. Okay, so now we know what a structure for the signature of categories is, and we want to see how we can formulate the univalence condition given in that Ahrens, Kapulkin, and Shulman paper in a way that is easy to generalize for any structure. Okay, so the way we do that is as follows. So we want to kind of formulate just the notion of isomorphism in terms of our structure. So we remember from our studies of the neonatal lemma that an isomorphism between A and B can be given as a class or a system of isomorphisms between Hom sets like this that are natural. And so naturality can be written in terms of our signature like this. So we just write this out in a square, you'll see that's expressing naturality for these phi's. But this is a bit, this is expressed in terms of our of the things that we've considered in the structure of our category, but it's a bit ad hoc and not symmetric. So we can just observe that we could, instead of considering all of these Hom sets, we can also consider all of these Hom sets and all of these Hom sets, and also equalities not only between these two predicates, but also all of these predicates. And if you look at this for a while, you'll see that what's happening here is that we are looking at all of the predicates, A, T, I, and E, that live over O, and we're kind of, say, making a hole in each one, and replacing first A in that hole, and then we're replacing B in that hole, and then we're stipulating that those should be equal. So we're kind of replacing A and B in holes in every way that we possibly can. And we can say that if that doesn't make a difference to all of these types, then everything kind of above A and B thinks that A and B are the same. So we cannot discern A from B using any of the constituents of our signature A, T, I, or E. So we cannot tell the difference between A and B. And we call this an indiscernibility. So I won't define it in general, but I think you get the idea. And then we can say that a structure M of a signature L is univalent if the type of indiscernibility, so a collection of all the equalities like this, between any two terms of any one sort is equivalent to the type of equalities between them. And I have not defined the word sort yet, but a sort is something like this. So this is a sort of objects. This is a sort of arrows between X and A. This is a sort of identities on F, and so on and so forth. Okay, so if we impose the requirement that a structure be univalent, this in particular means that all the top level sorts are going to be propositions, and all the next level sorts are going to be sets, and after that they're all going to be groupoids, and so on and so forth. So let's see that for the example of categories. So let's consider any of our top level sorts. So this is a CI for a given F, or the equality predicate for an F and G, and so on and so forth. So any two elements, let's say, of this guy are indiscernible, because we said that indiscernibility means that nothing above this sort can tell the difference between any two guys, the two guys that we're thinking of. But there's nothing above this sort, if you remember, in our signature. There's nothing above I. So of course we cannot tell the difference between two elements of CI of F using things in our structure. So those are indiscernible. And so in general, any two elements of a top level sort are going to be indiscernible. So all of these guys are going to be, if we want the structure to be univalent, these will all be propositions. Okay, now I won't get into the details, but if we impose axioms that are making E a congruence for T and I, and we want to know what an indiscernibility between two arrows is, then it just boils down to equalities between F and G. So basically, E is kind of the finest relation on arrows. And so this is the type of indiscernibilities between F and G. And so if we impose the requirement that our structure is univalent, that means that the equality type between F and G should be the same as these weird equalities between F and G, so in the end nothing weird is happening. But that in particular means that since we're stipulating that the equality type has to be a proposition, which we discovered up here, then the Ham type is actually going to be a set, a Ham set. Okay, and then going down a level, we just saw that the type of indiscernibilities between any two objects is just a type of isomorphisms between them. So to make a structure univalent, we're going to impose this equality between the equalities between A and B and the isomorphisms between A and B, and this is going to make O a groupoid, CO a groupoid. Okay, so as suggested, the univalent LCAT structures are exactly the univalent categories that were described in this paper by Ahrens, Kapulkin, and Shulman. Okay, so the whole point is that we want to have this univalence principle for categories, and so in order to generalize this, we also have to generalize the notion of equivalence. And we do that by notating that with this, or noting that with this framework, a equivalence of categories is just a very surjective morphism of these structures. And what very surjective means, what the very there means, is that we have a surjection between each of these sorts. So at the bottom level, at the object level, we have just a surjection between the types of objects. And then at the next level, we have a surjection between the type of arrows from x to y and the type of arrows from fx to fy, and so on and so forth. This carries through to surjections between all of these. Okay, so now let's generalize this story and talk about what's happening in the general case. So we can define an equivalence between two L structures to be a very, not only a very surjective morphism from M to N, but we actually need, for technical reasons, a very split surjective morphism from M to N. Categories are a particularly nice example where we can get rid of the splitness condition. And now our main theorem says that given any two univalent L structures, M and N, the equality type between them is going to be the same as the type of these equivalences between them. And as another kind of corollary, we have that given any signature of height n, so the sig n means that it has height n, the type of univalent L structures is of h level n plus 1. So we can see what we would expect there. All right, now, as I said in the paper, we have lots of examples in the preprint on the archive. We have lots of examples. These are some of the more interesting ones. Here for each of these different concepts, we've worked out what the indiscernibilities are that fall out of our theory, and then also what the equivalences are. So for duploids, for example, we have that the indiscernibilities between negative objects are linear isomorphisms, and between positive objects they're thunkable isomorphisms. And then an equivalence between duploids is just what you would think a normal equivalence of categories between the two sides. That on the negative side is just up to, it's an equivalence up to linear isomorphisms, and on the positive side it's an equivalence up to thunkable isomorphisms. For premonoidal categories, the indiscernibilities are just central isomorphisms, and the equivalences are equivalences up to central isomorphisms. For thunk force categories, the indiscernibilities are thunkable isomorphisms, and again we see that the equivalences are equivalences up to thunkable isomorphisms. So I mean normal categorical equivalences up to thunkable isomorphisms. For bi categories, we see that the indiscernibilities of zero cells of the objects are internal adjoint equivalences, and the equivalences of bi categories are strong bi equivalences. For symmetric colored operads, the indiscernibility of objects are just the isomorphisms, and the equivalences are just the normal notion of equivalences between symmetric colored operads. We also have looked at the example of double bi categories. Their indiscernibilities of objects are invertible companion pairs, and the equivalences are a bit long-winded, so I would suggest that you check out our paper on that. All right, so in summary, we have given a notion of signature, and for every signature we have given a notion of indiscernibility within each sort, a notion of the univalent structures of that signature, a notion of equivalence between structures of that signature, and a univalence theorem equating the equalities between two univalent structures and the equivalences between them. And that automatically gives us a higher structure identity principle for any one of these structures. All right, thank you, and I look forward to your questions during the conference. Thanks.